Okay, good afternoon. We've seen several talks talking about the status of the different DDoS attacks, and in this talk I will try to present you with the architecture and the methodology to defeat DDoS attacks and something we believe the internet should employ to protect itself. My name is Yehuda Afek. It's a joint work with Anat Bremler-Bar, Alon Golan, Hank Nussbacher, and Dan Twito. I'm affiliated with Tel Aviv University, and we all work at OneWall. So let's first discuss what are the types of, oops, well, the animation doesn't work. Something wrong about the presentation. What went wrong? Okay, I don't know, something went wrong with the transparencies. We've seen in the tutorial yesterday and some of the talks today, some approaches to defeat DDoS attacks where we use the routers, different routers features such as the ACLs, rate limiters, and the most effective one is to route the victim's traffic to null zero. All of these methods, they do solve the good packets together with the bad packets. So actually we saw just before the lunch an approach where you send all kind of BGP rejects, and actually what you did, you helped the attackers, because as soon as you start the attack, you disconnect the server or the target of the attack. So actually the attacker just needs to make the noise as if he is attacking, and boom, the target goes off the internet. So that's the main problem with those approaches. Another problem is that routers don't always have the necessary CPU power to handle all these techniques when they are heavily loaded with the DDoS traffic. So another approach you could think of is to build a special device that knows how to sieve out the bad packets from the IP stream and leave the good packets going through, and employ it at the edge right before the victim or the potential victims. Obviously, and those that have been in NANOG already over a year, we saw the talks by Steve Belavin and others, this approach won't work because it's too close to the target, and say in this case if we have a 500 megabits attack, the line going just into the bottom router is choked, and even if you have a supercomputer in front of the target, it won't be able to solve the problem. The strongest computer in the world won't help you over here. In addition, such a solution is not economical. You need to deploy special equipment for each additional potential victim, which is non-scalable. So, going with the recommendations of Steve and others, we move upstream, going towards the sources of the attack, and we deploy such a solution on the backbone links. This solution, we believe, has some problems because the device you now deploy needs to be a very strong device. It has to handle OC48, OC192 throughputs. It divides its attention. The computational power of the device is divided between the good packets and the bad packets and the non-victim traffic and victim's traffic, so you don't get the full attention to the victim. And it will be a long time before I convince any of you to put a new device on your backbone on the critical path. So what we get is what essentially we are trying to advocate here, is to deploy such a device that knows how to distinguish between bad packets and good packets next to strategic routers in your network. And the idea is that once victim is attacked, and you know that he's under attack, to divert all the packets whose destination IP address is victim, and only those packets through the device, have the device clean the traffic, and place the legitimate traffic, or what supposedly is legitimate traffic, back on its route to the intended destination. That's the general suggestion that we are advocating. As you can see, we don't add the device on the critical path. This solution lets the routers route. We need some help to do the diversion, but we don't ask the router to do the filtering. We don't use the ACLs. And you can place the solution as upstream within the premises of your network as possible. So you can employ it, as we'll see in the next slide, on peering routers or as far to the edge as you can push it. And it's a shared solution. You can protect with this system, with this platform, any device in your network. You can protect any of the potential servers that is connected to your network. You can protect the routers, DNS servers, proxy servers, whatever is routable in your network. And it's dynamic in the sense that you don't need to prepare anything extra before you can protect a new server. You don't need to make all kinds of preparations and installations to protect a new guy that's hooked up to your network. So, for example, one possibility to deploy the solution would be to put these special devices, washing machines that know how to wash the traffic, on your peering routers, or you can see one of them is at the access router. And when there is an attack, activate the diversion, have the washing machines clean the traffic, and let the legitimate traffic reach the intended victim, which is now not a victim anymore, and we can survive the attack. So just the basic principle is to divert the traffic, have a washing machine clean the traffic, and return the legitimate traffic to the intended destination. The whole process is activated, of course, by a detection mechanism. I won't go into the detection so much right now because we believe detection and protection are two different mechanisms that should be dealt separately when you deal with DDoS. There are quite a few detection mechanisms that we have seen already, and some new ones. I can talk about it in another time. Once the alert is getting to the mission control or the network operations center, it goes and activates the guards, the washing machines. Those signals usually will go out of band, and they will activate the diversion, clean the traffic, and save the victim from the attack. So the idea is, rather than black holing or taking all the traffic into a sinkhole, is to take all the victim's traffic to machines sitting on the side. You can see them as a distributed, one huge distributed sinkhole, clean the traffic and put it back, what's supposed to be the legitimate traffic, and have the victim continue to provide the service. The washing machine itself consists of several different lines of defense, or several different algorithms inside the box that know how to distinguish between the bad packets and the good packets and throw out the bad packets. Obviously, you have different filters, several anti-spoofing mechanisms to avoid the spoofed attacks, and you have all kinds of statistical methods working on the traffic after it has passed the anti-spoofing to recognize anomalous behaviors and to be able to block those flows that have been detected to behave anomalously. Most of this talk, for the rest of the talk, I want to discuss the ways to do the diversion. So the diversion really consists of two steps. One step is to grab the traffic, bring it over to your washing machine, and the second step is put the clean traffic back on the network, on its way to the destination. And of course, the key issue, without looping. You don't want the traffic to be rediverted and entering an infinite loop between the router and the washing machine. That's the problem we are facing that we have to deal with. So here is one simple approach to do the diversion. In case you have a layer 2 device attached to your router, which is the typical case in data centers, and some other switching offices have layer 2 devices next to the routers. In this case, you use BGP announcements from the washing machine to the router to divert the traffic on the address space which is under attack. It's a /32 or a /31, /30, whatever is being attacked. We do those announcements with the no export and no advertise community strings, so the announcement don't go any further but this router. And to return the traffic on its way to the destination, this machine, the washing machine, acts a little bit like a router, putting the traffic back to its next hop, the next layer 3 device on its route to the destination. So the traffic doesn't even get back to the original router. That's a simple method that works very nice. If you don't have a layer 2 device next to your router, here is another simple method to achieve this diversion, which is essentially was done already, was presented in NANOG 19 in Albuquerque by Wessels and Harty when they dealt with the popular content with the surrogate system. So again, you use BGP as before to divert the traffic, but now you open a channel to the next, all the possible next hops. So this washing machine is again acting like a router, but now routes over the one hop panel. It's actually two hops, one hop from the washing machine to the router, and then between those two routers towards the destination. Notice, however, that because of the way we do the whole scheme, the tunnel only carries traffic in one direction, so the bottom router only needs to do decapsulation. It doesn't do any encapsulation. And the work that he has to spend on doing this decapsulation is actually less than the amount of load he would have if all the DDoS traffic would just pass through this router. So you're just in a win-win situation. In any event, we noticed that doing this decapsulation increases the CPU load on the routers we have tested by at most 20%. We tested up to 200,000 packets per second. So we actually done several different tests. One of the tests we have here, 2 attackers and the client, 2 routers and 2 servers, one of them being victimized and the other one is a non-victim. And we have 3 phases for this test. Normal traffic with the green lines we saw a minute ago, an attack period, and then we activated the diversion, and we see the results over here. So the x-axis is the time, the y-axis is the latency in microseconds, and the latencies are measured from the client on the right, which was pinging both servers on the bottom. So normal operation, the latency was about 350 microseconds. During an attack, things are broke. You can see that many packets got lost, so they go off the screen. Some packets managed to get through. This is because our attack was staggered, was in bulks, and in between the bulks there were periods of quietness that has to do with the queuing phenomena, the way the attack was mounted. And the third period to the right is the time when we activated the diversion. And you can see the non-victimized server gets back to normal operation, no additional latencies. The victim actually suffers an additional 150 or so microseconds, which are due to the fact that its packets have still to go the extra hop through the washing machine, processing of the washing machine, and going back. So this is the gap here between those 2 lines. We have tested several other approaches for doing the diversion. One of them is WCCP. WCCP is a protocol coming out of Cisco. There is an internet draft describing it. The intention of WCCP was to help transparent caching. So you could have a cache machine instead of the washing machine, transparently talking to the router and asking the router, divert all port 80 traffic to me. The cache was handling the HTTP content and returning the traffic either to the client or to the server, depending whether you had the content. And it essentially does exactly what we want to do for protecting against DDoS. And actually, this, what I described, was the first version of WCCP. Version 2 of WCCP actually supports the version of different flows on different parameters. You could ask to divert traffic from certain destinations or certain sources or whatever parameters of the flow. And you can also do remote diversion. You could ask a remote router, divert the traffic to the cache machine / or washing machine, and return the traffic, and the protocol would automatically initiate a tunnel between the washing machine or the cache machine and the router. Notice the WCCP is not a configuration. You have to configure the router to be ready to talk WCCP, and then to activate and deactivate, it's a matter of a protocol. The main issue here is that it's available only on these routers down here, the 7000 machines. It's not yet available on GSRs, though Cisco promises to have it available on GSRs real soon. And it's available on these T-trains and the S-trains, some of the recent of them also with BSEF. Juniper, to the best of our knowledge, doesn't have something equivalent. Another possibility to do diversion, now it's requiring configuration, it's using policy-based routing from Cisco or filter-based forwarding from Juniper. Essentially, those are methods which override the routing decisions of the router. You can have rules, it comes with associated ACLs, and you can specify if it's traffic matching the ACL, route it differently, route it to this and this interface rather than routing it according to the routing table. So we could employ it on this interface card connected, say, to your peering link, and say traffic whose destination address is victim, send the traffic over here. When the traffic comes back from the washing machine, it will use the routing table, so it will go on the normal path towards the destination. Same thing with filter-based forwarding. Another approach to do the same, to use the policy-based routing or the filter-based forwarding, would be to employ it on the interface card connected to the washing machine. When you do it this way, only the traffic that was intended to the victim and only the legitimate traffic is going through the policy-based routing processing. Because this processing does require some CPU cycles from the router. You minimize those CPU cycles by employing it over here. All the traffic, the transit traffic, and all the rest of the world going normally over here. Only the clean traffic, after it's been cleaned, will go through the policy-based routing processing. As I mentioned before, it requires dynamic configuration to activate or deactivate an access list in order to start or stop the diversion. It increases the load like 20–30% depending on the throughput on either the interface card, the VIP, or the RSP. And Juniper probably will perform it better due to the dedicated Internet 2 processor, which is assigned for this job. We had really hard time getting policy-based routing to work for us. We did all kinds of experiments, and turns out there are different access lists, those that you can enumerate and those that you can give them names. And the access list for policy-based routing cannot be named, they can be only numbered. And we, for some reason, decided we wanted to give them a name and spent a few weeks, and there are all kinds of bug reports that what happens when you do those bugs, everything is being diverted, not only the traffic matching the access list. Okay, last diversion method that we are playing with is actually by using double addressing, or to assign an extra IP address to the victim. What you do, you divert the traffic as before with BGP announcement. Now to send the traffic back to the victim, you give the victim a new IP address, or you keep aside a separate and internal IP address just to route the traffic from the washing machine to the victim. Of course, you have to make sure that this IP address will not be used by the attacker, so you have to block this IP address on the boundaries of the protected area to make sure that attackers cannot use this kind of secret internal IP address to attack the victim. And in some configurations, to ease the management of the different IP addresses, you can employ NATs to do the translation from the IP address used from the washing machine, and here going back to the standard IP address that the victim is used to. So I have 5 minutes, I have to speed up a little bit. Another feature that can be worked out with this architecture is reverse protection. You could use this system, depending on the diversion method you are using, to protect somebody else's victim from being attacked by your customers. So if your neighboring ISP calls you up and says, hey, you guys, you're attacking my client, you could divert packets going to that client on the way out rather than on the way in, clean them, and only let the legitimate traffic going to that client and cleaning out all the attack traffic. So that's what we call reverse protection. It really depends on the way you do the diversion. And another something which is works very nicely with our architecture is providing this reverse proxy mechanism, or what people from Equinix call the surrogate system. You could attach a good cache server to each washing machine, and if the victim is actually not a victim of a DDoS attack, but he's becoming very popular, you give him services from those web caches on demand for the duration of its popularity, and if in 2 days he is not popular anymore, you go back to normal routing, and if another server is becoming popular, you activate the method to the popular subset of servers. So you can employ it on demand. So let me summarize the approach that we have shown you here. We believe using this architecture, you could actually keep the servers up and running rather than just routing to null zero or synchrolling them, and maximize the amount of good traffic or legitimate traffic reaching the destination and cleaning out the bad traffic. You don't put any hardware, any new devices on the critical path, at least not for the protection part of the DDoS. And we don't count the routers. We don't throw extra load on the routers to do the filtering and the sieving. We do it with the special devices that you put, or what we call them, these washing machines. As we said before, we can protect any device in your network with this architecture. You activate the diversion to the IP address which is under attack. And when you divert for a particular IP address, he gets the full attention of all those washing machines sitting around. Those washing machines are working fully to the set of victims which are currently under attack. You don't process non-victim traffic with those washing machines. So it's like a shared resource, large shared computational resource sitting around, and you give it to the victims that need it on demand when they need it. And of course, there is a way to deactivate. So when somebody is no more under attack, you sense that it's no more under attack and you stop the diversion. And we can live with we can use the principles that were advocated already years ago of being as upstream as possible, keeping the infrastructure of our network clean from this extra traffic. Okay, if there are any comments, we'll be happy to receive them. We'll be around here also for the rest of the meeting. We handle the questions now.
We got a few minutes for questions. You can come up to the mic. Remember to state your name and where you're from.
Livio Riccioli from Reactive Network Solutions. How do you wash the traffic? How do you tell what's a good packet, what's a bad packet?
That would require really lots of, let me see, it's over, what are we, 11. There are different algorithms that you can use in this washing machine. We have, it's really a whole collection of algorithms that it will take me way too long time to explain them. But basically, basic techniques that you use there is anti-spoofing. So if you want to use later statistical methods to identify anomalous behaviors, you have first to clean out the spoof traffic, because the spoof traffic can skew your statistics, and they can even generate things that look, they can destroy your statistics essentially. And different types of filters to deal with what you detected to be anomalous behavior, to block these compromised sources from generating any more traffic to the victim. But I'll be happy to talk to you offline. Each algorithm by itself we can discuss in depth.
In the back.
Avi.
Hi,
Hi.
Avi with Agamai. I have an observation. It was a really good catalog of all the different kinds of things you could do. And even though policy-based routing is really nasty and breaks sometimes, it may be better than some of the other approaches. One of my questions, I guess my main question is, with some of the first approaches, you have where you use two routers, one to take the, on the ingress to take the packets to the washing machine, and one to get them back in. You've now got two routers in your network which have inconsistent sort of direction about what to do with traffic to a prefix. And that's caused all sorts of problems, ranging from OSPF bugs when you have multiple LSAs that are different, or just the problem of managing that kind of configuration, especially in a dynamic routing environment. So I was wondering if you've used this on relatively large networks and what operators have said about having to manage that kind of thing.
I'm not sure I got the essence of the question, but essentially the thing is being activated. I don't know if I'm answering your question, Avi, but ask again if it's being activated by the NOC. Usually people will do it over out-of-band channels. And the washing machine itself, say using Zebra or some other code, talks to the router to activate the diversion. It talks BGP with the router.
So would you do iBGP just to one router, so
Yes.
that only that router has that?
Between the washing machine and the router, there is iBGP, and you have to statically, the tunnels, in case we don't have the layer 2 device, you need to configure the tunnels, but you configure it one time statically. You know, when you switch up your system, you don't need to play or to dynamically change those tunnels. You have to maintain them if things fail and recover, but they have to be there all the time. It's not a tunnel per victim or something of this sort.
Hi, Suresh from Ericsson. When looking at this washing machine, it looks like a terribly expensive piece of equipment. Say, probably it's going to do like line rate filtering on like n number of OC192. So, what is going to be the cost factor for this washing machine?
Well, you could use different vendors for your washing machine. I don't know, Maytag or Whirlpool. I don't know what kind of washing machines. But essentially, yes, it's an expensive piece of equipment. But the nice thing is that you can share it with all your customers. So you deploy, depending on your size, the number of steering points or the number of points you decide to deploy this solution, you can have small number of these devices protecting hundreds or thousands of customers. Some of them will pay for it, some of them will not pay for it. Notice also that if a customer that you don't want to protect, you could still use it as a sinkhole. You could divert the traffic, but not clean it, just throttle it or throw it out. You don't need to clean the traffic, but you still protect your network because you took this DDoS traffic out of your backbone.
Okay.